Day 17, page 315, number 57. This is a classic, what they call escape velocity problem. This is the velocity that you need at minimum to be fired at, to be shot at, to leave a planet or an object's gravitational field. It's related to its potential energy. For example, U sub g, the equation is negative g m sub 1 m sub 2 over r. You find out the minimum potential energy, and we'll do that here, but we'll have to do it in terms of m2, our unknown mass that we're firing here, because you might suspect that it doesn't really matter what the mass is, but I'll just leave it in here now. Or you can pick up mass, 5 kilograms, 10 kilograms, as long as you're consistent. You'll see how it cancels out. But once again here, you're going to have negative g, which is negative 6.67 times 10 to the negative 11th times the mass of the moon, 7.4 times 10 to the 22. I'm going to call this m sub 2, then I'm just going to leave it in there, divided by the radius of the moon, 1.74 times 10 to the 6th. And let me pause and get that with my calculator. And that comes out to be 2.8 times 10 to the 6th m sub 2 joules. So m sub 2 is the mass that you'll see cancels out. Once again, it's negative 2.8. So that's your minimum energy. So what happens is as the rocket goes higher and higher, or the object goes higher and higher, that number goes less and less negative, so it increases. And the maximum it can get is 0. So we need to put in 2.8 times 10 to the 6 joules of positive kinetic energy to launch this object at the minimum. If we give it extra kinetic energy above and beyond the 2.8, like if I give an object, say, 3.0 times 10 to the 6 m sub 2 joules of energy, that's an excess of 0.2 or 200,000 joules of energy, that would be left over for the rocket to continue on with some velocity after it has escaped. In that case, it would be basically a constant velocity after that. But bottom line is, if I have a kinetic energy equal to that, of positive 2.8 times 10 to the 6th, that's the break-even point, m sub 2 joules. That's where the rocket will go up, 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 and then stop at infinity. So now I just set that equal to kinetic energy, which is 1/2 mv squared. In other words, 2.8 times 10 to the 6th m sub 2 equals 1/2 m sub 2 v squared. So the m sub 2's will cancel out. And that's why it doesn't matter what that was. So basically multiply the 2.8 times 10 to the 6th times 2, and then take the square root. That gives you the escape velocity from the moon. I'll let you do that.